Hello everyone, I'm Vaggelis from White Noise, the student rocketry team of the National Technical University of Athens. We're currently developing Project Aurora, the first sounding rocket designed and built by undergraduate students at our university. At the heart of it all lies Avionics. To ensure precision, reliability, and mission success, we design custom PCBs tailored specifically to our rocket's needs. That's where EasyEDA comes in. EasyEDA is a powerful electronic design platform that integrates schematic capture, PCB layout, simulation tools, and component libraries all in one seamless environment. Its intuitive interface allows our team to move efficiently from concept to schematic and from layout to manufacturing-ready files without friction. In this video, I'll show you how we design our BME280 sensor board using EasyEDA, along with some quick tips to help you get comfortable with the software. Before we start, make sure to download the application from the link in the description below. Now, let's begin. Click New Project to get started. Choose a name for your project and select the location on your computer where it will be saved. Every PCB design starts with a schematic. In the schematic, we define all the electrical connections of our circuit, usually by carefully studying the component's datasheet. Since we're designing around the BME280 sensor, you can pause the video here and quickly look up its datasheet to understand what is required for it to operate properly. Next, we import our components using the library icon shown on the screen. If you don't see everything highlighted in the red box, don't worry, these are custom libraries created specifically for Project Aurora. We'll explore those in future videos. For now, go to search bar and type BME280, select the correct component and click Place. And just like that, it appears in your schematic. For this tutorial, we'll design a custom breakout board from schematic to PCB to integrate the BME280 into our system. There are multiple categories inside the component library, which makes navigation easy. Since I already know which connector I need, I'll search for it directly. Originally, we wanted a 4-pin connector, but for demonstration purposes, we'll modify the 5-pin version instead. Place it into the schematic. Press space to rotate if you need. Then, right-click on the component and select Edit Device. As you can see from the screen, the technical details of the connector are now customizable. I press Pin and I remove the extra one. Always press Ctrl+S to save. Now, if we return to the original schematic, you can see the updated connector matching exactly our needs. The BME280 communicates via I2C, which means the SDA and SCL lines require pull-up resistors. Why? Because I2C uses an open drain architecture. Devices can only pull the line low, they cannot drive it high. So we need pull-up resistors connected to VCC to define the high logic level when the line is not being actively pulled low. So, we will add 2 pull-up resistors from SDA to VCC and from SCL to VCC, as you can see here. We set their values according to the datasheet and system requirements to 4.7 kilo-ohms, and then we connect the respective wires. The other 2 pins are for VCC and ground, so the voltage that will power our board and the ground. You can insert ground using the arrow icon shown here. You can press left click as you place the wire to prevent it from rotating during placement. As you can see, mine rotated, so we press left click, set it, and connect it. We know that CSB must be tied to VCC for I2C mode selection, so we connect it accordingly. And ground connects to ground. Always keep your grounding clean and consistent. Now moving on to labeling, which is mandatory for proper collaboration and PCB readability. Click Label in the side panel and assign names to each net. From this panel, you can rename the connections to match your system architecture. Clear labeling avoids confusion during PCB layout and debugging, especially in team environments. SDO and ground are connected according to our address configuration to ground. The power pins go to VCC, but to improve power stability and reduce noise, we add decoupling capacitors between VCC and ground. These capacitors help filter voltage fluctuations and ensure stable sensor operation, which is critical in high vibration environments like rockets. Connect the ground on the opposite side of the pin and the VCC on the side of the pin of the sensor. And with that, we've completed the schematic design. To start the PCB layout, click on PCB on the left side of the screen. The PCB workspace will now load. Next, go to Design, Import changes from schematic, click Apply changes, and now you can see all the components from the schematic placed inside the PCB editor, ready to be arranged and routed. At this point, you might notice that the component H1 still has 5 pads. That's because its footprint is still associated with the original 5-pin connector. To fix this, right-click on the footprint and select Edit Footprint. Inside the footprint editor, delete the 5th pad. Then, remove the corresponding mechanical lines from the component outline one by one. After that, adjust the body outline so it matches the correct 4-pin connector geometry. Always press Ctrl+S to save. Now when we return to the PCB layout, the footprint correctly matches the schematic. In our designs, we typically use the square pi to indicate ground for clarity during assembly. In this case, however, that's not currently do. To correct this, we go back to the schematic, copy and paste the 4-pin connector, then right-click and flip it vertically and now return to the PCB editor. You'll notice that the square part still does not correspond to ground. That's because we haven't synchronized the schematic. So now that we go to design import changes for schematic, it does correspond to ground. Now, something interesting happens. You'll see that the 4-pin connector appears again as a 5-pin version. Why? because earlier we applied the footprint change only locally, as you can see, not to the entire project. The original library definition was not updated globally, so the schematic re-import restored the original footprint mapping. Since the previous edit footprint instance was deleted during synchronization, we need to edit the footprint again, just like we did before. So we right-click, select Edit Footprint, remove the fifth pad, adjust the outline, and press Ctrl S. And now the footprint is correctly synchronized with the schematic. Now that we pressed Apply to the entire project, any new 4-pin connector we copy and paste will automatically be linked to the correct footprint, as you can see here. That ensures consistency across the whole design. Now, suppose we delete this, we are ready to route everything. The blue lines you see are called the route lines. They indicate electrical connections that still need to be physically routed. We'll start with the data lines, SCK and SDA. You can press the spacebar to rotate components for better alignment before routing. If we route one trace directly, the other might cross it. We want to avoid unnecessary crossings, especially on a 2-layer PCB. So, we select Route, Single Track, Single Routing. We'll keep the default 10 mm track width for the signal lines, at least. Now we begin routing. This is where PCB design becomes a bit of a puzzle. We're trying to route the most efficient way possible, minimizing crossings and keeping traces clean. That's also why we adjust pin orientation in the schematic. Good schematic decisions make routing much easier. For VCC, we increase the track width to 15 mm. Why? Because power traces carry more current, and slightly thicker traces reduce voltage drop and improve reliability. The bypass capacitors must be placed very close to the power pins they're connected to. This is critical. Their job is to suppress high frequency noise and stabilize the supply voltage. If they're placed too far away, their effectiveness drops significantly, so we go back to the schematic to verify exactly which pins they connect to and move them physically close to those pins in the layout. So C1 is to pin 8 and C2 is to pin 6. Now we'll create a ground plane. Go to Place, Copper Region, Rectangle, select the bottom layer. Draw the region covering the board area. In the copper settings, after we draw the region. Now we'll change the connection type to direct. The ground plane reduces electrical noise, improves signal return paths, and simplifies routing. Now, we move to the top layer and make sure all the ground connections are properly tied in the ground plane. Next, we create another copper region for VCC on the top layer. Copper regions are essentially very large traces. They connect everything inside them electrically. You can see the created copper area highlighted in red. We also add additional ground regions at the top layer for better connectivity. And since this is a two-layer PCB, we use vias to connect the top and bottom layers. Vias are small plated holes that electrically connect copper from one layer to another. Place them strategically to tie the top ground regions to the bottom ground plane, as I will do in just a little bit. The final physical step is defining the board shape. Go to Place, Board Outline, draw the perimeter of your PCB, you can also add corner radius to smooth the edges and improve aesthetics. From the 3D preview, you can visualize how your PCB will look once manufactured. It's a great way to double-check component orientation, connector alignment, overall proportions. Before exporting, always run DRC, Design Rule Check. This verifies clearance violations, unrouted nets, overlapping copper, manufacturing constraints. For us, no errors, but if I intentionally disconnect something, you can see how the software immediately detects the issue and provides clear error messages. That feedback is extremely useful. The final step. Go to File, PCB Fabrication File. This generates the manufacturing-ready files which we can send directly to JLC PCB for fabrication. And that wraps up our introductory PCB design tutorial. From schematic capture to routing to copper planes and manufacturing files, this is the complete workflow we use to bring our avionics systems to life. Designing PCBs for rocketry isn't just connecting components, it's about reliability, precision, engineering discipline, because once the rocket leaves the launch rail, there are no second chances. We'd like to give a huge thank you to EasyEDA and JLC PCB for providing a powerful, intuitive design environment that allows student teams like ours to move quickly from concept to production and for turning our designs into high-quality manufactured boards with speed and precision. Being able to go from digital layout to a physical PCB in just a few days makes rapid iteration possible, and that's critical in an aerospace environment. With EasyEDA, we transform ideas into flight-ready hardware. Thank you for watching. Stay tuned for our next tutorial.